looked it up actually,
Mm-hmm.
and
Right.
there's one answer, but like I don't know, like I don't understand it. But it says if A, the answer, the A is n by n. They're assuming that.
Okay.
Uh, then if
Right.
A is singular,
All right. Okay. Let me just write the statement. So we are just trying to
yes.
prove, so recall ourselves, that this is equal to 0 if A is singular.
Actually, this one is for just adjoint of A is equal to 0 if A is singular. But I think it might like provide some insight.
Adjoint of A is 0.
Yeah, if A
No,
is singular.
no, that's not true.
No, no, sorry. I mean, adjoint of A is singular. Like it was a proof for that.
Okay, adjoint of A is singular, we have proved, right?
Oh, okay.
Right. So we have shown,
Oh, yeah. We use that. A adjoint A.
yes,
Yeah.
is singular.
Right.
But then we want to show that obviously adjoint of A is also singular, but we want to show that it's 0. It is the singular matrix. It's a 0 matrix, right?
So null.
Yeah, null matrix. Okay. So yeah, I mean, I was thinking about this, and I don't think we can do this. Yeah, I mean, it
Right.
is true, but I don't think it is. So basically, we need. Uh, the way I feel is this: that yeah, uh, just a minute to say. Yeah, so can you see that it is is it computationally viable? Like, does it look any? No, right? Computationally, it seems like it's just mess, right? If you
Yeah, like I was
uh,
thinking, like maybe you could just write down A and then adjoint A, but like yeah, it becomes a huge mess.
a huge matrix, and if you want to show that determinant of something is zero, but in the end you want to show, just a minute, the determinant of something is 0, and that, and so let's think about it. I'll try to say what I can say. I mean, I this can be done, but we need a bit more quantitative information. Just something being invertible or something being singular, these are two opposite ends of the spectrum, but there are a lot of things in between also which one can consider, and maybe using them you can try to show. Okay, so let us just have a look. So let us say that this is adjoint of A. Okay, now we are saying that the adjoint of this is the 0 matrix, right? We want to say that this is 0 0 0 everywhere. Okay, you can imagine 3 by 3 if you want, but then to compute the adjoint of A, okay, or to compute the adjoint of any matrix, what are you doing? You are, for example, what is this entry? Yeah, this entry is the determinant. So this is x, right? Then this x is basically the determinant. Let's call this b, right? Then let's call this small x, right? And small x is basically determinant of b. Agree or not?
Yeah, yes, sir. But like in general, we'll have that plus minus sign.
Right, yeah, that is
Yeah.
fine. That I'm not interested. It's 0, it is 0, whether
Yes.
it's plus 0, minus 0. So, yeah, and we want to show that this is 0. Okay,
Yes.
which
Yes.
means, yeah, which means you want to show that this matrix is actually singular, right?
Yes, sir.
Right.
Yes, sir.
So, now if you want to show that this is singular, Okay, and not just this is singular, right? But you want to show basically that any n minus 1 cross n minus 1 block of this adjoint of A, looking at this matrix adjoint of A and looking at any n minus 1 cross n minus 1 block, right? We want to show that it is 0. Its determinant is 0.
Yes, sir. Yeah.
Right? The true. So this means we want to show that this means that we want to say that not just that adjoint of A is singular, but every block is singular. Every block of adjoint A is singular, right? So in summary, what I want to say is that adjoint of A is much more than just a singular matrix, right? Adjoint of A is more is very singular, meaning that every n minus 1 cross n minus 1 block is singular. Okay, am I saying that every n minus 2 cross n minus 2 block is singular? No. You can see the difference, what I'm trying to say, right? Like if you look at this kind of matrix, it is singular, but every 2 by 2 block is not singular.
Yeah, like because by definition we're deleting one row and one column. So n minus one, n minus one will come.
Right, but that is not singular in this case. For example,
Yeah, yes.
but in this case, we are saying for adjoint of A, they are singular. Okay. Now the problem is that when a matrix is singular, and then you want to say that every small block n minus 1 cross n minus 1 block is singular, or you want to say that every k by k block is singular, right? Now that kind of becomes a complicated statement. Then block of block is singular and so on. So we have to find another way to talk about it. And that has to be the rank of a matrix. Okay, rank of a matrix. So what am I talking about? It is not nothing complicated actually. So um, so far, what do you know? You know that B is singular. I mean, just in general, B is singular means that determinant of B is 0. Okay. But you see, this doesn't really, I mean, this doesn't really say anything actually, in a way, right? What determinant of B equal to 0 means is that there exists some constant C1, C2 till whatever, if it's n minus 1 cross n minus 1 matrix, such that C1, R1, R1 is first row vector, C2, R2, dot, dot, Cn minus 1, Rn minus 1 is equal to 0. Right? So if you take any matrix B, so first you tell me if you agree with this or not. You look at R1, look at R2. If you look at how you really compute the determinant or uh, or how you invert a matrix, then you know this fact that B is singular, meaning it doesn't have an inverse or its determinant is 0. Yeah, this is same as saying that there is a relation between the rows. Okay, you can multiply the first row by some constant, scale it, and then similarly scale it so that it is 0, and obviously one of the constants is non-zero. Do you see this? That is the first question.
So like I don't fully see it, but like I somehow like I
So you can kind of see it, right?
right.
So
Yes.
you can think about it in terms of linear independence of vectors and volume of what determinant gives volume, right?
Right,
In
right.
geometric direction, you can see. I'm not going to be precise about it. You can think about that. So I'm not going to prove this. This is not difficult. But another way
Yeah.
to think about this is, another way to think about this would be that that if you have a matrix B, right, then you can basically do row operations, right? You can do row
Yeah.
operations, and whenever you do row operations, then you don't affect the linear independence of the rows. Okay, so if you have some rows R1 to R1, R2, R3, let's say 3 by 3 sitting there, okay, and you do one of those row operations which you know, right, then whether those three were independent, meaning that whether these constants existed or not, that fact doesn't change before and after applying the row operations at every step, and hence it doesn't change in any finitely many steps, right? But if you apply this finitely many times, then the determinant being zero or non-zero doesn't change. Okay, so so all those information don't change. And if you apply it finitely many times, then you get a very simple matrix which has some ones and then some zeros on the diagonal, and everywhere else zero. Right? I No, I mean, sorry, this is not correct. Yeah, it is correct in a way, but if you only apply on the left, then you can basically make a matrix like this. Okay, where you do zeros in the bottom, and here you will have some numbers, right? And then from here you can see whether or not, right? I mean, if you don't get these zeros, right, it means you only get ones. Then you know that this is invertible, right? And then you know there is literally no relation you can think of. Then for this kind of matrix where it is one, then there are no relations, right? So the fact that whether there was a relation between the rows doesn't change. So we can only be concerned about the relation between the rows of the last matrix that we get. The last matrix is very simple. If you get this kind of matrix that doesn't have any relation between the rows, you can see that. Yeah, you have to have all the CIs to be zero in order to make the combination zero for this kind of matrix where the lower triangle, lower part is zero. Okay. So if you get this, then yeah, then there is no relation, and this obviously determinant is non-zero. And if you do get zero here, relation zero, which then there is a relation. Yeah, you can check that out, that there is a relation, because you can take C1 equal to 0, C2 equal to 0, and here till here you can take Ci equal to 0, and here you can just take Ci. You can yeah, work that out. You can do it. Okay, basically then this will be, yeah, then you have a relation, and that you have a relation here, which means you had a relation to begin with, because the fact whether you have a relation or not doesn't change. Okay, although it's somewhat vague. I mean, this is sort of like first five classes of or maybe let's say at least first three classes of linear algebra in BSc 1, BSc first year. Okay, yeah, at least three. This is, I just tried to cram it in few lines. But anyways, this is the fact, and this fact one has to use. Okay, so okay, now the point is that then this becomes a okay, number of linearly. So basically, we see that the rows are, so B is single. So this basically now we mean saying that B is non-singular. Okay, we'll come to the problem. So B is non-singular means that it means that there is no relation, which means that if there is a relation, that implies that this Ci is equal to 0 for all I, right? It's the same statement, there's no difference, right? So what I've just said is that B is non-singular, B is invertible, determinant is not 0. It means that um, the rows, as we say this, are linearly independent. So the number of linearly independent rows is n. All the rows are linearly independent. When you come to singular, it means that all the rows are not linearly independent, right? There is a relation. Okay. So then we ask to know how non-singular a matrix is. We ask, okay, all the rows are not linearly independent, but can I throw away one or two rows or some number of rows so that my resulting smaller set is linearly independent? Okay, so here so rank comes in the picture. Okay, rank of a matrix is number of I mean, it can probably be defined only in terms of determinants, but if I define it like that, I will have a tough time proving what I want to prove. Number of linearly independent rows. Maximum, you don't have to be very precise, but because they'll all turn out to be the same, maximal or maximum number of linearly independent rows.
So, sir, rank of a singular matrix is 0.
No, it's less than n.
Oh,
Get it?
okay.
Right?
Oh, right.
Right? So
So
if
it's
you look
at
at,
most n, at most n. Yeah.
yeah, but if it is singular, then it is not n. It cannot be n, right?
Right.
Because the rank was n, it means that all are linearly independent, which means that this happens, which means there is no
Okay.
relation. Any relation is a trivial relation, which means it is non-single. Okay, so basically that's the thing. I mean, something becomes singular, dominant vanishes, means that the area becomes, volume becomes 0. It means that the rows are dependent, right? So how many are dependent? Then we look, that helps us to break down the class of singular matrices. And most matrices are singular, right? Very few matrices are non-singular. Most matrices will have determinant 0. Or is that correct? No, I mean, okay, sorry, that's a nonsense statement, right? Yeah, but yeah, you can make out whatever you want. Yeah. Anyways, that was some wrong thing. Completely wrong thing I said. Sorry. But yeah, okay. We want to now look at the which have this thing. Okay. So what we want to now say about coming back to this, right? We are basically now saying that this determinant of B is 0, right? Determinant of B is 0 means what? Determinant of B is 0 means that the corresponding rows, right? It means that these corresponding rows, yeah, they are linearly dependent. There is a relation between them. Yeah, the rows of B have a relation between them, right? Okay, so right, and so we just want to say that if you look at the adjugate of A, okay, so pay attention to this. If you look at the adjugate of A and you look at the rows, you take any n minus 1 rows, okay, its determinant is coming out to be 0, right? So any n minus 1 rows, the determinant is 0, which means that any n minus 1 rows are linearly dependent, right?
Right. Yes, sir. So that's what we want to show.
Correct. That is what we want to show,
Right.
right?
Okay. Yes, sir.
Right. And if we can show that, then we are done, right? If we can show that, then we are done. So we basically, okay, then it will be done, right? So we basically want to then show, so because from here, that is what we are getting, that, okay, that's the kind of thing we should show, that any n minus 1 rows are linearly dependent. Okay, which means that the rank is n minus 2. Okay, which means that the rank is uh, correct, yeah, which means that the rank is n minus. So for the it's not about this anymore, right? It's all in this now, right? The adjugate of A, any n minus 1 rows, the determinant is 0, is what we want to show, which means that any n minus 1 rows are linearly dependent, right? So the maximal number of linearly independent has to be less than n minus, but it has to be n minus 2 or maybe n minus 3. So we want to say that the adjoint of, the adjugate of A has rank less than or equal to n minus no, that's not correct. Yeah, less than or equal to n minus 2 if A is singular. Fine. This is what we want to show.
Yes, sir.
Okay, so I have introduced a new concept, and that is quite a bit unfair if you are, I don't know, it's a, if you can handle that. But it is fine. I am not saying anything in a complicated way. So we want to show that. I don't know how to show this though. Okay, so yeah, so A is singular, which means that the rank of A is n minus 1. Okay, then the rank of adjugate of A becomes 1 less. So that's a good thing about adjugate, right? That it doesn't just take a singular matrix and gives you a singular matrix, but it actually brings the rank down. So that's a nice thing. So why is the rank? Yeah, so you want to show that. Yeah, you want to show that any n minus 1 rows are linearly dependent. Either you show that or. So adjoint of A, we understand it's a standard matrix. You can also try to use this. You can also try to use this once again. Okay, you can also try to use this. Yeah, back to the same identity. So try to use this.
Sir, I actually found someone saying that the rank of the adjoint is the same as the rank of A. Like, and they've given a proof for it. I don't know.
Okay. Okay, then 1 minute. Then what we are doing is wrong. So if rank of adjoint of A is same
Yeah.
as rank of A.
Oh,
No, but that cannot be
they've given
correct. That cannot be correct.
no,
If
they've given a note. They've said that there appears to be an ambiguity in terminology. To me, the adjoint is the complex conjugate of the transpose. So, like I don't know. Yeah, so I think they're talking about something different.
no,
Yeah,
complex conjugate you
like
can remove, but transpose is. Oh, no, no, no. Oh, that is completely different, man. That is a different thing. Yeah, right, right. That is just taking
right.
transpose. That is just transpose with conjugate.
Okay,
Yeah, that there the rank remains same. That is just saying row rank is same as column rank. That's a theorem. That's a different thing.
right.
But
Okay,
that's
sir.
also easy to prove using that Gaussian elimination. No, no, no. Here the rank
Yeah, yeah.
goes down. Here the rank goes down. Let us try to prove that. Uh, this is an interesting statement. I've surprisingly never done this question. Look, if A has rank n minus 2, then you are done. Agree?
Right. Yes, sir.
If A already had rank n minus 2, then actually adjoint of A would be 0 by the same reasoning. But let's explain that. So if A had rank n minus 2, it means that any n minus 1 rows are linearly dependent, right? Yeah, if A has rank n minus 2, it means that any n minus
Yes.
1 rows
Yes,
are
sir.
linearly dependent, which means their determinant is 0, right? So every determinant you calculate while calculating the adjoint will be 0, right? If A has rank n minus 2. Right.
So I actually found something.
Okay.
So this person is saying the rank of adjoint of A equals 0 if R, that is the rank of A, is lesser than n minus 2, where n is the order, and the rank of adjoint A equals 1 if R equal to n minus 1, and the rank of adjoint A equals n if R equals n. So that is
Okay.
what they're
Yeah. Yeah.
saying.
Yeah. Yeah. So that is again that is something more stronger which he's saying. Okay.
Yes. Yes, sir.
Yeah. 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 But actually that will be what we'll prove in the end. So the R equal to n minus
Okay.
2
Okay.
case is this basically. So first
Yeah.
do you see why this is true? So if the rank is n minus 2,
Yeah.
it
Yes,
means,
sir.
yeah, so any n minus 1
Because of the
rows,
n minus 1, we can take any n minus 1. They'll
yeah,
be dependent, so we'll have 0.
determinant will be 0. So, and those
0.
that
Yes.
is what the entries of adjoint of A are. So that is done,
Right. Yes, sir.
right?
So
Now,
yeah.
right, but then when the rank if A is equal to n minus 1, that we want to then show that the rank of adjoint of A is n minus 2. Okay, so
So,
we just, what?
this person is saying if rank of A is n minus 1,
Mm-hmm.
then rank of adjoint of A is 1, like not n minus
Yeah, but
2.
we don't need that statement, right? We don't need that song statement. That,
So we want to show that it's lesser than. Right.
yeah, we will. I just want to show it is this. Okay. And he's
Okay.
saying that it is 1, which
Right,
is
right, right.
obviously
Oh, because
his
it's
set.
maximal. Okay, okay, yeah.
Yes, right.
Maximal number of rows. Yeah, I
Yes,
was
yes, yes. So
forgetting that.
yeah, yeah, because you're doing this for the first time. Yeah. So rank is 1 means
Right,
that any two are linearly dependent. Okay. Which is
right.
which is nice. And this is actually what I will show then. Okay. So in fact, the strongest statement sometimes easier to prove. So now basically, but let's do this. So then we are basically saying that rank of A is n minus 1. This is the case we have to consider,
Yeah, yes,
right?
sir.
And now you see in this case, it's very simple because this means that there is a matrix B which you can multiply on the left of A, and B is invertible. Okay. Basically, I'm saying that B is invertible. Okay. And BA looks like this. It has ones in all the rows except that the last row becomes 0. Whatever. You can, and this I'm not commenting on this part. Okay, I mean I yeah, so these are 0. Okay, and these I'm not commenting on. You can do this. This is basically that row column operations, if you are willing to believe this. Okay, or you can see it like this, that basically starting with any matrix say you can apply the row column operations, right? And you can finally get a matrix which is upper triangular, right? And on the diagonals you have ones or zeros. Okay, the number of ones on the diagonal is the rank. The rank doesn't change in the process, right? Something is a dependent or not doesn't change if you apply those simple row operations. Okay, this is again a theorem, this is not a okay thing, but this you can do. I think you will need this. Now it is easy, I suppose, because now you can multiply with B. that B. And B is invertible, so it doesn't really hurt anything. Okay, so now BA times adjoint of A is equal to 0. Okay. Hmm. So what? So what? So basically, this is the matrix, and this times adjoint of A is equal to 0. And now what can we say? You want to say about the rows. That, so let us try to show that the first n minus 2 rows or something. Yeah, right. So when you take the, no, sorry, nothing. Let us do it systematically. So I want to show that a Ising rank of adjoint of A is 1. That's actually can be easier to prove. Yeah, that is actually easier to prove, right? So I mean, yeah, I mean, either ways, even if I don't assume that I can prove it. So now just look at this. So you have this, right? This is, let's say this is what adjoint of A is. Okay, let us say this is what adjoint of A is. Okay, yeah. And then what happens? What is the product? Well, you take 1 times R1, okay, and you take this dot times Rn, right? So this R1 plus dot times Rn. That's what the first row is, right? And what is the second row? Okay. What is the second row? Second row is 1 times R2 dot times dot 2 maybe. Okay. R2 plus dot 2, whatever, right? Times Rn. Do you guys believe me? Right? This is what is happening, right? This is how the
Correct.
multiplication
Yes, sir.
works.
Yes.
Yeah. And then this
Yeah.
is 0, 0, 0, which means that R1 is equal to dot times Rn. R2 is equal to dot times Rn. So everything is a multiple of Rn, right? So R1, R2, Rn minus 1 are just fake. They are all Rn multiples of Rn, right? So this is some multiple of Rn, maybe 2 times Rn, and this is some 3 times Rn. Okay, so there is only one row actually. Others are all dependent on it, right? Yeah. Yeah. So this matrix is just one row and other rows are multiples of it. So how can 2 rows be linearly independent or 3 rows be linearly independent? It's impossible, right? They are all multiples of one thing. Okay, same thing. That's all. This is it. So actually the rank is 1. And even if you don't know that, you will actually end up proving it, provided you have this gadget with you. That this is all analysis of Gaussian elimination gives you this. And then yes, then basically you can. So yeah, I mean there is, yeah. So how, what do I have to say? Anything else? Yeah, A times adjoint A is 0 means that B times A times adjoint A is 0. And this is, yeah, that is it. I don't have to say anything more. So yeah, this problem is a little interesting. Basically, everything boils down to that Gaussian elimination, which we can talk about next time in this. Okay, right. All right, then let's stop here and we can discuss about the next class sometime later. Aryan, what time would be okay
Yes.
for you about the exams and so on? That's
Uh,
what I'm asking you.
so like my next exam is on 24th and it's just computer exam. So like even if I have it, I can attend for like 1 hour, one
Oh,
and a half
okay,
hour.
so then what would be the next good date for both of you?
So any date you fix, any date
Friday
you give,
9
I'll
p.m.
attend.
Friday 9
Right.
p.m.
Yes, sir.
Nagesh, is that
Yeah.
fine
Yeah.
with you?
Yeah, sure.
Friday 9 p.m. Okay, so Friday 9 p.m. we will not be doing matrices. Okay, we will be doing some problem solving. Okay,
Right. Yes,
just
sir.
the ISI-CMI level if you guys have, and if you don't have, then I will do some problems. Okay, all right.
Right. Yes, sir.
Okay,
Yes, sir.
bye. Bye.
Okay,
Good
sir.
night.
Yeah.